Hello, we're starting the Year 12 course with Topic 1, which is Basic Physics. This is an overview of some of the simplest ideas and some of the skills that you'll need as you move through the various topics in the rest of the course. It's quite a large topic because there's obviously quite a few skills we need to introduce and a few ideas as well. So the specification there, if you want to pause and read through it, feel free. And in today's lesson, we're going to be looking at the first 3 points, starting with SI units. So SI units are part of what's known as the System International, which is a worldwide recognized system of classifying quantities that everyone can then recognize, and therefore it makes physics international and provides a symmetry across the world. We have 6 quantities we need to know, and I've included the 7th. So the first one is length. Obviously, there are other terms that could be used for this: height, distance, separation, and so forth. And that is always measured in meters. We also have mass, measured in kilograms, the only one that always requires a prefix. We have time, which is measured in seconds. We also have electrical current, which is measured in amperes or amps. Some of you will have already encountered the unit for temperature if you did triple science at GCSE. All temperatures now should be measured in Kelvin, which is just a slightly different scale to Celsius. We also have something you will probably be familiar with from chemistry: amount of substance, which is measured in moles or mole. And the last one, which isn't on the course but does complete the set, is luminosity or luminous intensity. And that is measured in candela. So these are our simplest units. They can't be broken down any further than that. And these are the ones that are referred to worldwide, and all other units stem from these. So this brings us on to derived units, to give you an idea of where the SI units fit into this. And it's these derived units that you need to be able to check for homogeneity to show that an equation is correct. So we can start with a simple one just as an example. If we look at force, now there are various equations for calculating force. I'm going to go with the simplest form of Newton's second law: mass times acceleration. Now we know that force is going to be measured in newtons, but newtons isn't an SI unit, it's a derived unit. So it comes from the SI units, and to simplify them, we've just bundled the SI units together and given it another name. So the mass would be measured in kilograms. The acceleration is going to be in meters per second squared. And therefore, kilogram meters per second squared are the SI or base unit of a Newton. They are essentially the same thing. So when we use that term Newton, or if we was to say 7 newtons, what we actually mean is 7 kilograms meters per second squared. But obviously that takes a lot longer, so we've simplified it by creating this new derived unit called the Newton. But you will need to be able to show what a Newton is in SI units. So your first task is to find out what we mean when we refer to these SI units. So I've included a worksheet, which is illustrated in your assignment. And what I'd like you to do is try and find some scientific definitions for these 7 terms. What is it that we actually mean when we refer to 1 meter? Now, these aren't just your simplistic ideas like defining 1 second as a 60th of a minute. They need to be true scientific ideas, things that are universal and do not change under any other circumstances. So you will need to look online and find some proper definitions of what we mean by these SI units. Moving on from definitions, we're going to look at now at how we can find the SI units for derived units. So we're going to look at the standard equation for kinetic energy. As you should know, any energy is measured in joules, or J. But this is not an SI unit. So we need to use the right-hand side of the equation to find out the SI units for joules. So one of the key things for this is any simple numbers have no units. So they can be ignored when we're looking at the units. Mass would be in kilograms, and velocity will be in meters per second, ms to the minus 1. But because it's squared, that becomes meters twice and per second twice. So the SI units of a joule would actually be kilograms meters squared per second squared. Again, moving on from that, then looking at another unit for power. So we can apply what we've just looked at. So energy would obviously be in joules, power would be in watts, and time would be in seconds. Now we know this to be true from our definition of power, where 1 watt would be the equivalent of 1 joule per second. So this equation does work with derived units, but we'd also need to be able to work out the SI units of power. It's all about just balancing your units. So joules would be kilograms meters squared per second squared, would be the equivalent of watts multiplied by seconds. So in order to balance this, those watts must be kilograms meters squared per second cubed. Now, any of these numbers, when you're using the equations, can have prefixes, just like at GCSE. So I included a copy of a table of prefixes. These, as with GCSE, are supplied for A level, but it helps become familiar with them. But they do not carry any units. So even if you were doing something simple like speed equals distance over time, if the distance was in kilometers and the time was in seconds, then your speed would be in kilometers per second. Now, that's not a standard way of doing speed, but obviously as speeds become greater, sometimes we have to include prefixes. So when you're looking at planetary motion, obviously the planet's moving at vast speeds, and using meters per second doesn't become appropriate because the numbers are too high. But that kilo in there does not impact the SI unit at all. It's just a multiplier, or any prefix is a multiplier or a divider. So prefixes have no impact on the overall unit. It only affects the data part. So the last part of this lesson, we're going to look at homogeneity. Okay, so homo comes from same, okay, like homeostasis, keeping things the same, and geneity means gene or origin. So when we're looking at equations, we need to make sure that everything in the equation is of the same origin, and you have to be able to show this. Now, in exams, it is standard to have an equation that is homogeneous, because anyone would be able to muck it up and show it's not homogeneous. So it's all about proving that the equation is correct. So wave speed, we know, is a speed. So our standard SI units would be meters per second for this. Our standard unit for frequency is hertz, and our standard wavelength would be meters. So the meters are dealt with. The meters balance on both sides, so it's homogeneous in terms of that. But the hertz and the per second don't seem to, because they're different. But if we remember, our definition of frequency was waves, or for GCSE, waves per second. Now the waves was just context for the GCSE Year 10 topic of waves. The actual frequency is per second, or something per second. So the SI unit of hertz is actually s to the minus 1. So this equation would be homogeneous because we have the same amount of m's on each side and the same amount of per seconds on each side. Looking at a slightly more complex equation then, so in the Suvat equation, so this is part of the A level, but only part of the GCSE if you did triple science. So we have an equation where we have distance. U is the original speed, or original velocity. T is time. Half is just a half. A is acceleration. And T, again, is time. However, we have this plus in the middle, which makes it slightly more complex. Now, for this equation to work, all three sections need to be homogeneous. So whatever the units of x are, ut have to have the same units, and half at squared has to have the same units. Okay, so we're looking at x is meters, and when we compare that to ut, u is speed, so in meters per second, multiplied by time, which would just be in seconds. So the per second and the second cancel out, leaving meters. So that part is homogeneous. We then look at the half at squared. The half disappears because it's just a number. Acceleration is meters per second squared. And t is seconds, but that is also squared. So again, the per second squared and the second squared cancel, leaving just meters. So that is homogeneous. Okay, so anytime you've got a plus or a minus, it breaks the equation up, and the next section also has to be homogeneous for that equation to work. So to round off this lesson, I've put another task for you on the assignment to see whether you can show whether equations are homogeneous or not. Have a go at that along with your definitions task and let me know if you have any problems.